Hello everyone, I'm Sebastian Y, and this is Managerial Economics. In this video, we're going to talk about isoquants and their shape using the marginal rate of technical substitution. An isoquant is a curve that connects the combinations of inputs that yield the same level of output. Isoquants for production functions are analogous to indifference curves for utility functions. Just like indifference curves, there are an infinite number of isoquants for every production function. We have an isoquant for every possible level of production. Moving along an isoquant shows the substitutability of labor and capital. The marginal rate of technical substitution is the rate at which a producer can substitute between two inputs and maintain the same level of output. Remember that we have two inputs, labor and capital. We can do the MRTS going from labor over to capital or capital over to labor, but I'm going to always use the MRTS of labor for capital, meaning we're getting a little bit more labor, giving up a little bit of capital. Mathematically, we're going to define that as the MRTS of labor for capital, so I'm going to put subscript LK here, equals the marginal product of labor divided by the marginal product of capital. Notice that this looks very similar to the marginal rate of substitution of x for y over when we did utility, which was the marginal utility of x divided by the marginal utility of y. Back when we did that, I mentioned that we could flip everything and have the marginal rate of substitution of y for x. We can do the exact same thing over with the MRTS and flip everything, but what that means is that you have to make sure that if you do that, you flip everything later on. For that reason, I'm always going to stick to MPL over MPK. How we can think of this is that we are going to increase labor by a little bit. That's going to give us a little bit of marginal product of labor, but we're going to give up a little bit of capital, and that's going to lose us some production. And the ratio of these two things tells us the rate at which we can do that and maintain the same level of output. Because I'm always going to do things labor for capital, just like I did x for y, I'm always going to put L on the horizontal axis of graphs, just like I did with x, and K on the vertical axis, just like I did with y. Again, you could flip everything if you want, but that's how I'm going to do it. What this all means is that the MRTS will be the absolute value of the slope of the isoquants. To illustrate all these points, we're going to go through how to calculate the MRTS for our three different production functions. Let's start with the linear production function. This has the form f of k and l equals ak plus bl. In the previous video, we showed that the marginal product of labor is b and the marginal product of capital is a, which means that our MRTS of L for k is going to be b over a. Since b over a are just constants, that means the MRTS is also going to be a constant. This also means that the isoquants for the linear production function are going to be straight lines. The slope is going to be the same regardless of the current level of k and l. Let's return to our example production function, which was f of k and l equals 3k plus 2l. This means the MRTS is going to be 2 over 3. Let's take a look at what our isoquants would look like. We have q equals 3k plus 2l. We can then plug in whatever number we want for q and then graph those isoquants. I'm going to draw a graph with L down here and K up here. Let's draw in a few different isoquants. Let's try Q equals 30. The equation of this isoquant will be 30 equals 3K plus 2L. The easiest way to graph a line like this is to figure out the intercepts. So if L were 0, we would get 3K equals 30, so that means K would have to be 10. If K were 0, then we have 2L equals 30, meaning that L would have to be 15. I'll use a blue line to graph this. This is going to be our isoquant for Q equals 30. Notice the slope of this thing is negative 2/3. This corresponds to the MRTS we calculated earlier of 2/3. Now let's suppose Q is 60. Our equation will be 60 equals 3K plus 2L. We can do the same thing here and figure out that our K-intercept would have to be 20, and our L-intercept would have to be 30 this time. We can draw in this isoquant for Q equals 60. We'll do one more for Q equals 90. Here the K-intercept is going to be 30, and the L-intercept is going to be 45. And we can go ahead and draw that in. Again, notice that each of these isoquants are straight lines, and they are parallel to each other. The higher the quantity, the farther out the isoquant has to be. These are not the only isoquants. These are just 3 of the infinite number that there are for this production function. There are more isoquants in between, there are more isoquants further out, and there are more isoquants further in. We will now consider the Leontief production function. Leontief production functions are of the form f of kl equals the min of ak and bl. In the last video, we talked about the fact that one of the marginal products is always 0 with the Leontief production function. Since the MRTS of labor for capital is the marginal product of labor over the marginal product of capital, if the marginal product of capital is 0, the MRTS is infinity, and if the marginal product of labor is 0, the MRTS is 0. Since the MRTS is the absolute value of the slope of the isoquant, this means that at any given point, the isoquants are either horizontal or vertical. This just depends on what the current ratio of labor to capital is. We've already established that efficient production with Leontief can only occur if capital and labor are in the specific ratio of B units of capital to A units of labor. Since there's never any reason to use inputs in any ratio other than that predetermined ratio, the MRTS is irrelevant to decision making. The isoquants for Leontief are L-shaped. The corners of all these L-shaped isoquants will lie on a line defined by AK equals BL. All of these corner points are combinations of inputs in what we think of as the correct ratio. Let's look at our example f of KL equals min of K and 1/2 L. Plugging the numbers into this equation right here, the corners of the isoquants will lie on the line K equals L over 2. Let's draw some of these isoquants. We're going to put L down here and K up here. I'm going to draw in a line that represents our K equals L over 2 line. Let's start with an isoquant for Q equals 10. The efficient way to produce 10 units of output will be to have K equals 10 and 1/2 L equals 10, which means L will be 20. Graphing this out, we have something like this, where the corner of the isoquant will be right here, and then the isoquant will have an L shape. To see why this is, remember that if we have 10 saws and 20 lumberjacks, adding more saws, that's capital, will move us up this way, but that will still result in exactly 10 units of output because those extra saws aren't doing anything. Same thing here. If we have 10 saws, but we start adding more than 20 lumberjacks, that still won't do anything. That's why all of these points along this blue L shape produce exactly 10 units of output. Let's do another one with Q equals 20. Here, K will have to equal 20, and 1/2 L will have to equal 20, which means that L will equal 40. We'll graph that in, 20 and 40. And that one will look like this. Just like with linear, we can keep adding more and more and more of these if we want to, but all of these isoquants will have an L shape with the corner lying on our line K equals L over 2. Finally, we're going to take a look at the isoquants for Cobbdouglas, which has a functional form K to the A, L to the B. In the previous video, we found the MPL equals B K to the A, L to the B minus 1, and the marginal product of capital was A k to the a minus 1 L to the b. This means our MRTS of labor for capital will be bk to the a L to the b minus 1 divided by ak to the a minus 1 L to the b. We'll now simplify this using the rules for exponents. We have a k to the a on the top and a k to the a minus 1 on the bottom. The k to the a's will cancel, and the same thing with the L to the b's. That's going to leave us with b L to the negative 1 over a k to the negative 1. The rules for exponents tell us that if we have a negative exponent, we just move it to the other side of the fraction, so we end up with bk over a L. Let's take a look at our example, which was f of k and L equals k to the 1/2 L to the 1/2. To calculate the MRTS, we could go ahead and plug the 1/2s into this right here, and we'd get 1/2 k over 1/2 L. The 1/2s cancel, and we just get k over L. In this case, it comes out very cleanly because a and b are equal. Of course, if a and b are not equal, it won't look quite this nice. We can also do this generally using the marginal products that we solved for in the last video. So MRTS LK equals 1/2 k to the 1/2 L to the negative 1/2 over 1/2 k to the negative 1/2 L to the 1/2. The 1/2s are going to cancel, and we're going to use our rules for exponents to move the negative exponent terms to the other sides of the fraction. So we're going to move the k to the negative 1/2 up to the top and the L to the negative 1/2 down to the bottom. So we get k to the 1/2 times k to the 1/2 divided by L to the 1/2 L to the 1/2. When we're multiplying these terms with the same base, we can add the exponents. 1/2 and 1/2 just adds up to 1, so that's going to give us k over L, just like we got from the formula. Either way you do this will get you the same answer. Now let's take a look at the isoquants. Remember that the MRTS is going to be the absolute value of the slope of the isoquants. Since the slope depends on k and L, that means it's going to be changing, and so we have a curve instead of a straight line. The equation for the isoquants is going to be Q equals k to the 1/2 L to the 1/2. To help us graph this, we could solve for k. Divide both sides by L to the 1/2. We get Q over L to the 1/2 equals k to the 1/2. Square both sides, we get k equals Q squared over L. This is actually a hyperbola. We could plug in any quantity we want for Q and go from there. For example, if Q were 5, then our isoquant would have an equation k equals 5 squared over L, or k equals 25 over L. I'm going to sketch a graph of this. My hyperbola graphs are definitely not going to be perfect, but with this particular isoquant, you could see that 5 and 5 will be one of the points along that. The isoquant will look something like this. Notice these look very similar to the Cobbdouglas indifference curves that we worked with previously. As such, they're going to follow those same rules. They're not allowed to bend back like I'm drawing here. So we're going to get rid of those. We could do another one. For example, if Q equals 10, then we're going to get K equals 10 squared over L, or 100 over L. 10 labor and 10 capital is going to be a point along this isoquant, and I'm just going to go ahead and sketch that in. As with indifference curves, I don't expect these isoquant sketches to be perfect, but you want to get them looking about right. As with all isoquants, the farther out we get, the higher quantity we have. So this one corresponded with 10, this one corresponded with 5, and so on. One thing to note about the shape of Cobbdouglas isoquants is that generally getting a good mix of inputs is the more efficient way to do things. You can see on our red curve here that using a relatively moderate amount of both, capital and labor, gives us the same amount of output as having a smaller amount of capital but an extreme amount of labor. We'll leave it there for now. In the next video, we're going to talk about the isocosts, bring those together with the isoquants for cost minimization.